Dear students, today's lecture is going to be very interesting, and an important question will be discussed in this lecture. That is very important question according to paper point of view, exam point of view. And the question is that Hesse's law of constant heat summation. That is the most important question. One is the Born-Haber cycle and one is the Hesse's law of constant heat summation in thermochemistry, which is usually asked in the paper. Now Hesse's law, it was presented by G.H. Hesse in 1840. I will move a little bit slower because it's very important topic so that you can understand it easily. Now the amount of heat evolved or the amount of heat absorbed during a chemical change is same whether the process is occurring in a single step or the process is occurring in multiple steps. Means if the reaction is completing in one step, if the reaction is completing in different steps, many steps are involved, even then the heat of the reaction or the enthalpy changes in these reactions or formation or breaking, it will remain same. Secondly, it can also be defined as the heat of a reaction depends upon only the initial state and final state of the system, and it's totally independent of the path followed. It doesn't matter the reaction is carried out in a single step or the reaction is carried out in multiple steps, but only it will depend on the initial state and the final state, and it will ignore all the multiple steps, intermediate steps which are occurring during the process. This is called as Hesse's law of constant heat summation. A general example, that is, if we want to convert A into D directly, the heat of the reaction in this process. The second method is if we want to convert A into B, the process is occurring in multiple steps. Then B is converted into C and then C is converted into D. In this case, the heat of the reaction for reaction number 1 is delta H1, second is H2 and third is H3. Now the summation of all these will be equal to delta H, that is H1 plus H2 plus H3. Now if we see the delta H for converting A directly into D and the delta H converting A indirectly into D with intermediate steps, these both are same. So according to Hesse's law, that delta H for A into D and delta H for these all steps in which A is going to D with the intermediate steps, these will remain same. That's called basically the Hesse's law of constant heat summation. Now if you want to experimentally verify this law, that the heat of reaction in single step is equal to the heat of the reaction in the multiple steps, then experimentally you take the example of carbon dioxide. It's the formation of carbon dioxide will occur in two different methods. One is direct method, another is indirect method. In direct method, carbon is converted into carbon dioxide, in which 393.5 kilojoule of energy is released along with a minus sign which shows energy is released. Indirectly, it will occur in two different steps. When carbon react with limited supply of oxygen, it will form carbon monoxide. In this case, 110.8 kilojoule of energy is released, and another case is carbon monoxide again react with limited supply of oxygen to form carbon dioxide. Now in this case, the amount of energy released is minus 282.7 kilojoule. We will add both the reactions and we will come to know that carbon monoxide will be cancelled in both the reactions, because in one case it is on the right side and the second case it is on the left side. Cancel both of them and the final reaction is carbon plus oxygen will go to carbon dioxide, and when we add the energies of both of them, we will get the total value, that is delta H is equal to minus 393.5 kilojoule. It is clear from this experiment that when the reaction is occurring in a single step, that is carbon is reacting with oxygen to form carbon dioxide and the amount of energy released is minus 393.5 kilojoule, and when the reaction is occurring in multiple steps, then again the amount of energy released is same. It proves that Hesse's law is right. That is, the reaction is occurring in a single step, if the reaction is completing in different steps, the amount of heat evolved or the amount of heat absorbed will remain same. It doesn't depend upon the intermediate steps, but it only depends upon the initial and final states of the system, and it is independent of the path followed by the reaction. Now the heat of formation of carbon dioxide, you see, it is same in both the cases, which is the experimental proof of Hesse's law. Another example is conversion of sodium hydroxide into sodium carbonate Na2CO3 by the reaction with carbon dioxide. Now in direct method, sodium hydroxide will react with carbon dioxide and it will form sodium carbonate plus water. In this case, minus 89.16 energy that is released. This amount of heat is released in the formation of sodium carbonate. Now you will see that indirectly the reaction is occurring in different steps. Indirectly, sodium hydroxide will react with carbon dioxide. It will form sodium bicarbonate. In this case, energy will be released, that is minus 48.06, and in second case, the sodium bicarbonate reacts with sodium hydroxide to form sodium carbonate along with water, and in this case minus 41.0 kilojoule of amount of energy is released. When we add both the reactions, you will get the final reaction that NaHCO3 will cancel with NaHCO3, and the final reaction is NaOH combined with carbon dioxide to form sodium carbonate and water. And when we add both the values from reaction number 1 and reaction number 2, we will get the final value, that is minus 89.06 kilojoule per mole. Now if we see in the case of direct and in the case of indirect method of formation of sodium carbonate, the amount of energy released is same. This shows that experimentally Hesse's law is verified. There are some applications of Hesse's law, in which the first one is to find out the heat of formation. Heat of formation is basically the amount of heat evolved or absorbed when 1 mole of a compound is formed from its elements. This heat of formation is denoted by delta H along with small f. Hesse's law can be used to determine the heat of formation for those compounds which cannot be synthesized directly from their elements in the laboratory. So in this case, Hesse's law will identify the heat of reaction of individual steps, and then finally you will add all the individual steps in order to get the net reaction, and in this way you can find out the heat of formation of all the steps indirectly. That is the application of Hesse's law. Now the Hesse's law can also be used to find out the heat of combustion of those substances which cannot be measured directly. And why they cannot be measured directly? Because of the following two reasons. Number one is combustion is too fast, combustion is too slow, or the combustion process does not occur cleanly. So in those cases, Hesse's law can be used to find out the heat of combustion of those substances. Example is burning of carbon in the presence of oxygen. Number one, if it burns directly or if it burns indirectly, we'll discuss both the steps. In direct method, carbon reacts with oxygen to form carbon dioxide, and the amount of energy released in this case is minus 393.5. It is basically the formation of carbon dioxide as well, and it is the heat of combustion of the carbon as well. For carbon, it is combustion because it reacts with oxygen to form carbon dioxide, and for carbon dioxide, it is the formation of carbon dioxide. So you will write the single reaction in both the cases, for formation and for combustion as well. In case of formation, you will tell that it is the heat of formation of carbon dioxide, and in case of combustion, you will tell that it is the burning, or that is the combustion of carbon in the presence of oxygen. Now indirectly, carbon reacts with limited supply of oxygen to form carbon monoxide. The reaction will evolve minus 110.5 kilojoule of energy, and in second case the carbon monoxide formed will again react with limited supply of oxygen to form carbon dioxide, and in this case minus 2 He 2 kilojoule of energy or 283 kilojoule of energy is released. We will combine both the reaction. Carbon monoxide will cancel with carbon monoxide, and the net reaction is carbon plus oxygen to form carbon dioxide, and the amount of energy when we add both the steps, amount of energy released is minus 393.5 kilojoule. That is called basically the heat of combustion of carbon in presence of oxygen. Now in both the cases, if you see, in case number 1, in direct step minus 393.5 kilojoule energy is released, and in case of indirect formation or combustion, again the amount of energy released is minus 393.5 kilojoule, and that is the experimental measurement of heat of combustion when the heat of combustion is not measured directly.